In this video, we will explore one of the special relativity effects. As you may remember, in the previous video we saw that the speed of a moving object will generate two important effects, time dilation and length contraction. But, these effects will become apparent only when the speed of the object becomes an important fraction of the speed of light. Time dilation is the lengthening of the time interval between two events, for an observer in an inertial frame that is moving with respect to a rest frame. Let's explore the time dilation effect. Imagine the following experiment. You are traveling in a spaceship moving at constant speed, and have a device composed of two parallel mirrors, separated by a distance d, a light source that you can control to turn on and off, and a timer. In some way, you turn the light source on, and one ray of light enters the space between the mirrors. You can see that the ray of light will bounce up and down. Using the timer, you can measure the time that the light spends in a complete cycle, and you call it delta tau. As light travels at a constant speed c, the complete cycle will represent 2 times the distance d. It is important to note that delta tau is measured in an inertial reference frame, and the experiment happened at the same place. We call delta tau the proper time. Now, let's repeat the same experiment, but this time, one of your friends is observing from the Earth. The experimental setup is the same. In order to avoid confusions, the time measured in the timer by the observer at the Earth is called delta t. Don't forget that the spaceship is moving with constant speed v. Now, we should ask, what time will your friend observe in the timer at her position? For your friend at the Earth, it's clear that from her reference system, the mirrors are moving with the spaceship. Then, the first ray will travel up in an oblique path, and will reflect, also in an oblique path. Notice how the lower mirror will change position by an amount v times delta t. If we analyze the path of the rays in a separated fashion, we can see that we have a triangle with one of its sides equal to the displacement of the device during delta t. Let's call S the upper sides of this triangle. It is clear that S is related to the length of the base of the triangle, and the separation between the mirrors. Don't forget that one of the Einstein's postulates is that light travels at the same speed, independently of the direction and the observer. Then, we can set these three equations. It follows from the geometry that finally, we obtain the relationship between delta t and delta tau. This is one of the major results of special relativity. It states that the time in the spaceship, observed from the Earth, will be elongated with respect to the Earth. In other words, the clock will tick slower in the ship than the one at the Earth, always that your friend observed from the Earth. Oh, by the way, you will see a normal ticking in the ship. We can make this expression more compact by using the factor gamma, also known as the relativistic factor. Let's solve an example to see the application of this equation. Example 2. What is the speed at which the relativistic effects become apparent? Suppose that you can measure time up to 1% precision. Hint: do the calculation assuming that delta tau is 1 second. Answer: as stated by the problem, we can use delta tau equal to 1 second. Also, as we can measure up to 1% precision, we set delta t equal to 1.01. In this case, we need to calculate the speed of the moving object from the time dilation equation. This means that by solving the equation for the speed, we get introducing the values of delta tau and delta t, the equation is the following. Finally, we get. This result means that in order to observe the time dilation effects, up to 1%, we need a speed of the order of 10% of the speed of light. In order to understand how huge this speed is, we should say that it is about 30,000 kilometers per second. This speed should be enough to complete a trip around the Earth in 1 second. Up to this point, we have discussed how to get the time dilation equation and its application. However, there are very important implications that should be discussed. When using the time dilation equation, we need to be very careful on two important facts. 1. The reference systems must be inertial, as special relativity doesn't work when accelerations appear. And 2. The proper time is the one measured in the reference system where the events happen at the same place. On the other hand, when analyzing the time dilation effect, it always appears the so-called twins paradox. Imagine that a pair of twins have decided to test the time dilation, and one of them boards a spaceship that will travel through space, at a constant speed, large enough to perceive the relativistic effects. The other twin will remain in the Earth. When the traveler twin comes back to the Earth, he should be younger than his brother, as predicted by the time dilation equation, right? Well, the paradox appears when we think of the relativity part. Because, the time dilation is relative to the observer. For the twin at the Earth, the traveler twin is moving very fast and dilating his time. But, for the traveler twin, his reference system is fixed at the spaceship, and the Earth is the one moving at high speed. Does it mean that special relativity is not working? Actually, the last statement is true. As stated before, special relativity only works over inertial reference systems. In the case of the twins, the traveler twin needs to accelerate to reach the relativistic speed, meaning that its reference system is not inertial. Then, when the traveler twin comes back to Earth, he is actually younger than his brother, as the Earth is an inertial reference system. In 1905, Einstein understood the limitations of his relativity theory. Actually, he spent about 10 years to complete a theory where accelerations were included. It is called the general relativity theory. It is an amazing piece of human knowledge, comparable in importance to Newton's theories. In fact, Einstein corrected the issues of Newton's theory of gravitation. In the next video, we will study the second effect, the length contraction. Stay tuned.